If you have no questions, let's start the class today. So we were discussing expectation maximization, and then I will try to relate this algorithm to the Gaussian mixture model training algorithm, right? And I try to say that in general, what we do in expectation maximization is the same thing what we do to maximize the likelihood in Gaussian mixture model, right? So I started with this scale divergence method. I said that this is a metric to find it out, like how given distributions are different, right? So this is like if there is two distribution P and Q. So I want to know how they are different. So you can find it out by using this formula, right? So if they are very equal to each other, exactly they are same, then you will get this value 0, right? So KL will be 0 for the given two distributions. And if they are different, then it goes to a very large number, and it depends upon how much that they differ to each other, right? Then I said that then we proved that KL divergence is always greater than or equal to 0, and we have discussed in detail yesterday, so I don't want to go it through. Then I came to this expectation maximization algorithm and said that this expectation maximization algorithm is used to maximize log likelihood function where we have latent variables also, right? For an example, sometimes we can bring latent variables. We can write log likelihood function this way or likelihood function this way. And similarly, if there are latent variables, we can write it in terms of joint probability and then marginalize over the latent variable. And again, we will get this distribution, right? Which is nothing but a likelihood function, right? So if we say that latent variable z, if we because we don't know the value and we want to infer what is the value, if somehow, and this is also known as complete log likelihood function because it is known as complete data log likelihood function when we know the value of z, right? Somehow, let's say somehow I get to know that value c, then you say I know the value of x, I know the value of z, and because I know both values, so it is not, then the likelihood function is complete, right? I know everything in it. But if you know the value of only x and not z, then this same distribution probability of x comma z, you can say it is an incomplete data log likelihood or incomplete data likelihood function, right? This is what we said. So incomplete is you said when you don't know the value of z, right? So in general, if you want to maximize it, so what we do, we just try to find out expected value of this thing because and then try to maximize it. Expected value, you know how to calculate it because I need to calculate the expected value. So then I try to find it out what is expected value, and because I don't know this thing, right? So I will try to find out expected value and then maximize it. We'll see it. Then I said that likelihood function, you can write it this way. Log likelihood function, you can write it as a sum of KL divergence and this lower bound, right? Right. So how I proved it, I started with this, right? And then I expand this thing there as a chain rule. And I do some like math juggling, and I found out that this actually holds, right? So yes, till yesterday we have done this. So then this equality says that log likelihood function is always equal to this L lower bound plus KL divergence between Q and P. And this Q is a distribution, right? This Q is a distribution which we have brought on our own. So it is like this. So this Q is a distribution which was like we can choose it as per our convenience here on this right hand side, and whatever this Q is, this equality will always holds. That's the point, right? This equality will always holds. The only thing is because both Q is available in these two terms, either this will get smaller and the other will get bigger, or other will get bigger and this second will get smaller. So there is a trade-off depending upon Q. For an example, as I said, this is a KL divergence here, right? So this is a KL divergence. If Q is equal to P here, then the KL value will be 0, right? Because I said that if the two distributions are equal, then the KL value will be 0. In that case, my log likelihood function x will be equal to this lower bound, right? Why I'm saying it is a lower bound? Because my KL divergence is always greater than or equal to 0. So if it is 0, then my L is equals to this log likelihood function Px, right? And if my KL divergence is greater than 0, right, then this L plus some positive number, right, will be equal to this value. So this L is always less than log likelihood function. So numerically, how can you see this? Oh, geometrically, how can you see this? So this red level is nothing but it is a log of x given theta, right? So this is that level, right? Let's say this is this level, and I say that it is a sum of KL divergence plus this value, right? If my KL divergence goes to 0, then this blue bar will go high till this red bar, right? And this L will be equal to log likelihood, right? If my KL divergence is not 0, then it is some positive number, and this blue line will always be below this red line, right? Hence, I am saying that it is a lower bound, right? It is bounding from the below. Is this making sense to you guys? Right? Yes or no? Right. Good. So then I say that this is a lower bound, right? So this is a lower bound. Fine. Okay. So what expectation maximization says in short, right? So you just read it on your own and you can have different perspectives. So I try to summarize it and so that it can just you can understand it in from this angle, and then you just read quite a few times and then you can derive on your own like what your understanding. You can develop your own understanding. So how expectation maximization you can see is this way, right? So you want to maximize this thing, right? You want to maximize this thing. So what I will do, I will to maximize this thing, what I will do, I will always try to maximize this thing, right? So I'm trying to maximize the log likelihood of x because I know this is a lower bound for log likelihood. So if I maximize this lower bound, definitely it will always be below to this log likelihood function. So how much I improved on this lower bound, it will always be below this likelihood function. So hence my likelihood will be always greater than this. So if I maximize this somewhere, I know that this log likelihood is greater than that. So indirectly I am increasing this thing, right? So there are two terms that come bring into the picture. So variational inference is a word which you may hear somewhere in your future, or there are so many deep learning models like variational autoencoders and all. They actually lie on this concept, right? So somewhere this is the foundation of the understanding those deep learning models and all. So what I'm trying to say that to maximize this log likelihood function, because this is a lower bound, if you indirectly maximize this lower bound, you can maximize this likelihood function. So now I just see this lower bound only, and because it is a functional and function, so functional it is for q and function is for theta. What I will do first, I will try to maximize this lower bound with respect to q, right? So in each step, we will try to maximize this bound with respect to q, and in m step, right? The second step will be m step. we will maximize the same thing with respect to theta, right? So there are two things, because this is a L and it is a function and functional for two very different things, functional for Q and function for theta. So in each step I will maximize it with respect to Q, and in MS step I will maximize with respect to theta, right? So if I maximize it with respect to Q, the direct thing will come is I should do Q such that this lower bound will get, this blue bar will should go high, right? The only thing that is stopping him to go high is the scale divergence here, right? There is a scale divergence sitting somewhere with positive value. If you bring the scale divergence to equal to 0, right? If you bring the scale divergence equal to 0, then this blue bar will go high and it will touch to this red bar, right? So indirectly, to maximize your lower bound with respect to Q, you want to minimize the scale divergence to 0. So what you can do in this scale divergence, you can make this Q equal to this P, right? Equal to this P, right? And what is this P? This is the posterior distribution over Z, right? This is a posterior distribution over Z. So for a given theta, if you make your QZ equals to P posterior of Z, then what will happen? You just put here QZ, rather than putting QZ, you will write PZ here, right? Because you have just replaced QZ with the posterior of PZ, right? Of x comma theta. X comma theta. Similarly, here in the denominator, PZ given x comma theta, right? Because now both distributions are equal, because you have intentionally done it. So it will cancel the above, because the both distributions are equal, and the scale divergence will get to 0. The moment you get to 0, your L will get maximized and it will be equal to this likelihood function, this red bar, right? So just to get in a sense like what we are doing in related to the Gaussian mixture model, because it is hard to visualize what is posterior here. So assume that in Gaussian mixture models, you had those initial assignments of thetas, right? So you said that I have some mean and I have some covariance matrices, right? I have some covariance matrices, and then I had some like prior values of pi1, pi2, and pi3, right? Those were the values of pi1, pi2, and pi3. So what I'm saying here is fixing these values pi1, pi2, pi3, theta1, theta2, mu1, mu2, mu3, and sigma1, sigma2, sigma3. You have freeze your theta. So you have fixed your theta, and then you calculate the posterior over Q, right? You remember how we were calculating posterior there? We were saying that it is, can anybody recall that we have calculated a posterior probability there in Gaussian mixture models? Is there anybody who can recall this thing? Only one student? You remember we were doing responsibility calculation there, and we said that the probability for generating this X is P1 from this, then P2 from the second cluster, and P3 from third cluster, and then finding out a posterior probability of cluster 1, right? So we said that probability of finding cluster 1, PZ1, given your theta is nothing but probability, what is a cluster 1 of generating X, and then what is the total probability, P1 plus P2 plus P3, right? We have done that thing. P1 plus P2 plus P3. So what you are actually doing, you are doing this posterior thing there, right? You are calculating the posterior probability over Z. So you do it for everything, Z1, Z2, and Z3, right? Then this is a distribution for particular nth sample, right? So if you want to calculate, because they are independent, if you want to calculate the total posterior probability, you need to multiply them, right? You need to multiply them because they were independent from I equals to 1 to n. From I equals to 1 to n, then you had a posterior probability for every sample. So you just made a posterior probability PZN given theta, because you have calculated posterior probability individually for every sample, right? This is how you can calculate the posterior distribution for this. And then you just say that this posterior distribution is nothing, but I am putting it with in place of this QZ, right? This posterior distribution, because I intentionally done that, then your QZ is nothing but posterior distribution, it will cancel each other. Okay, fine, very good. So I hope that I could have really like connected the dots for you. So what you were doing in Gaussian mixture model, so there, right? Okay. So in just to get back to the point here, what I was saying that I want to maximize my lower bound. So there are two things available here, Q and theta. First, I make theta fix and maximize my lower bound with respect to Q, right? If I maximize my lower bound with respect to Q, in that I need to make my KL divergence equals to 0. So the only way I can make it 0, I can just replace this QZ with the posterior of P, right? And hence it will get 0, and my likely lower bound will just be equal to the log this Px, right? This is what I have done. Okay. This is important. Just put this thing in your head, and let's go for the next second step. So it is a very subtle thing that are going to come. So you need to freeze this thing in your head, that right now you have maximized your lower bound with respect to Q, making your theta fix. So theta is fixed here, right? So let's say this theta, I just put it as old theta. This is old theta. And when my theta was old, I just maximize my lower bound. So then I need to calculate the posterior. So when I calculate a posterior, I use my old theta there, right? So I use my old theta there. And then I put this Q here, because this was also old here, right? This was also old, and this is also old, and they are equal there, and they cancel each other, right? So I have maximized my lower bound. Let's come here now. Now I have to maximize this lower bound with respect to theta, right? So if I maximize my lower bound with respect to theta, what I will what will happen is this, right? So you were there when you just made in your E step, you came till here, right? You came till here, but you are further maximizing your lower bound. So you are not minimizing, you are maximizing. It means you are raising the level, you are going beyond this level. If you go beyond this level, then your theta will get changed. So right at first you had old theta, because you are changing theta now. So in this theta will be new theta, right? This theta will, because if this get maximized by tuning these thetas, so your old theta will get changed, and let's say the new theta where it get maximized is new theta, right? So if I see this new theta, there in KL divergence in my previous step, I had Q old, right? It was old. And now I change my likelihood function, and hence it will change my theta. So if the moment I change my theta, so the moment I change my theta, right, my that Q will not be equal to this new posterior distribution of P, right? And hence the KL divergence will be non-negative, right? It will be some positive number, because this theta, old theta and new theta are not equal. Hence my in my previous step, which I made intentionally equal, they are no more equal now. Hence KL divergence will be some value which is greater than 0. The moment it is greater than 0, so my log likelihood effectively we get increased, right? So it was nothing but it was the probability of x given theta. X given theta. So in E step, I came till this bar, and then M step, I further maximized using theta. The moment I maximize my theta, maximize my lower bound with respect to theta, it increased the KL divergence. And because it increased the KL divergence, so the effective increment will be this increment, which you have maximized your lower bound with respect to theta, and this increment, because it just changed the value of KL divergence. So if you read this sentence somewhere, that the minimum increment in likelihood function will be this lower bound. So that minimum, because the moment you increase this bound, it will also give some KL value, and because you know the KL value plus lower bound will equal to the P, hence the minimum is this blue one, but the total is blue plus KL, and hence it will significantly get increased here, right? Until you are not at the maximum. Any questions still here in this concept? Feel free to ask questions. So I can understand this is right. This can be bit not very ordinary thing to you guys, but still, if you feel bit like uncomfortable, you can discuss it. Anyway, right. So okay then. So as I said that if we substitute my Q with this thing in this likelihood function, right? So so in my expectation step, right? E step, when I was putting my posterior QZ equals to posterior of P. So this is E step I have shown here. So in E step, if you replace your QZ with this posterior probability here, right? Sorry, just my. So when you do this, when you just replace this posterior probability in L, not in K, right? So because this is what you have said, right? Because you are replacing these things there. So in just to make this KL 0, you are replacing this Q with the posterior, right? You make this posterior. So the moment you make it posterior, you replace this Q with posterior, it will get 0. But here also, because you replace your QZ, so you have to replace here as well, right? You have to replace here as well. So this is that step. So in E step, putting your Q is equals to posterior will make K as 0, and what will happen to this L? So this is what we are discussing now. So if you just replace this posterior in L, what will happen? So it is just again bit simple mathematics. You're good at it. So you just open this log function, right? So it is a log A upon B is log A minus log B, right? And then what you will do, this is nothing but summation QZ. So summation Q ln P minus summation Q ln Q, right? This is what I said. So we said that you just replace this Q with the posterior. So you have to replace here this posterior. This is a posterior. This is a posterior. This is a posterior in L. And hence you will get this thing here. Right? You will get this thing here. Right? So this is the same thing, what it is written here. And you are maximizing in M step, you are maximizing this L with respect to theta, right? So because this is not at all depend upon theta, this second term here, it doesn't depend upon theta, right? Because theta is here available, right? This is the theta which is available here, right? This is the old theta which you have now don't have any control, because you have, this is that old theta which you have used to calculate the posterior, right? This is that thing. So now you want to maximize your L with respect to this theta. So this theta is appearing here only, right? So hence this second term will be a constant with respect to a theta, and you have to maximize this thing, right? You have to maximize this first term. So let's see carefully what is this first term now, right? So you want to maximize this first term. First, do you agree with me or not till here? Any questions or any confusion till here? Okay, very good. Very nice. So if you don't have any questions till here, so let's see this. So just in the beginning of my lecture, I said that we want to maximize the expectation of the incomplete log likelihood function, right? So here I don't know the value of z, right? So what is this? It is an incomplete log likelihood function, joint distribution, right? That we had that complete and incomplete thing, right? Can you recognize this? I have just said it in 2 slides before, right? This is an incomplete log likelihood function because I don't know z here. Then I say when I don't know the z value, so what we do, we want to maximize the expected value. So expected value is what? We are calculating we are taking some distribution over z. That's okay, it is a posterior distribution, but it is a distribution, right? So this is a distribution, and I am taking I'm having this distribution along with this function. What is this? It is expectation, right? It is expectation of log p x comma z. So if I want to write it, this blocked thing, so statistically, this is how I should write it. Expectation of log p x comma z given theta, right? Given theta with respect, so this expectation is with respect to which distribution? This is respect to this posterior distribution p z given x comma old theta, right? So this is old theta. So I want to have this expectation, I want to maximize this expectation with respect to theta, right? So hence it is known as expectation. First I'm calculating the expectation and then I'm maximizing it, right? So this L is nothing but you can see this L as the expectation. And if you maximize this expectation with respect to theta, this is known as expectation maximization, right? I should not write complete data log likelihood. It is it was not aware, I was not aware like what was my z, so it is like incomplete. And then that's why I'm calculating expectation of this incomplete log likelihood, and then I'm maximizing it. Fine. So this is all about to just making a dots of only expectation maximization. So if you have any problems, so I have just tried to tell you like why we say that it is expectation and maximization. So it is nothing but in short, if you want to say if you want to tell somebody, you say that if there are latent variables and we want to maximize my log likelihood function, then what you do, because there are latent variables, you don't know what is your complete data log likelihood function. So you just because now it is incomplete data log likelihood function, you calculate the expectation of that and then maximize it. And in that effort, whatever you will get, you keep on increasing it. So it is an iterative thing. Let's see why it is iterative. So before going on to the next slide, do you have any questions still here? Okay, no questions. Okay. So if you don't have any questions, let's see like geometrically how you see it. So this is my whatever. So first I will tell you how you can see these graphs here. Right. So this graph. So this graph, what we have shown here, right? This whole graph. You come to here. and just see this only this is instance of this vertical bar, right? This vertical bar here. You see this vertical bar here. So if you just put this vertical bar, so this is your red line log of px here, right? Then somewhere you may get log this blue bar, or might say just so this is my somewhere blue bar here, right? And this is nothing but a KL divergence somewhere. So this is my KL divergence. This is my lower bound. If you just remove your posterior, right? If you just take your posterior QZ equals to posterior, then the scale divergence will go away, right? The scale divergence will go away here only. So I am just talking about my old theta. So I am on old theta. What I did here, just I calculated a posterior distribution using my old theta, and I put it in equal to the formula. So the moment I put it into a formula, what will happen? KL divergence will soon go to zero. The moment it go to zero, this lower bound will directly touch to this red bound, right? So it also comes somewhere here. So this, because it just disappeared, right? So this lower bound will come directly and it touch to the red bound. It is just my old theta. Then I want to maximize my L, right? So then I want to maximize my L. So what was my L? So it was a function and functional. So this space, what it has shown you is in horizontal, there are thetas. So it is px versus, so log likelihood versus your theta only, right? So hence you keep on changing your theta, your likelihood will be keep on will get changed, right? Now if you maximize your L with respect to Q, so now I want to show you one other variable in the same space. So this is how we are showing it. So you change your Q, this blue curve will turn into a green curve, right? So this was your L, right? If you maximize your L with respect to theta, so this L is a convex function or concave function, you can see. The moment you maximize your L, you just see this blue graph here. So you maximize L with respect to this theta, you come here, right? Because theta will maximize here. So this is your new theta now. This is your new theta now. And this was the previous L bar, right? Log likelihood bar. And this is because you have maximized your lower bound. So either your log likelihood, this red bar will be till here or above than that. But I said that indirectly it also, because this theta will get changed, it will also introduce what? KL divergence into a picture. And hence the log likelihood function will be minimally the lower bound plus some KL divergence. So it will come now here. So in second iteration, again you make this KL divergence equal to posterior, right? And then this lower bound L will get increased here. And when you because you have changed only Q, right? So just because you have changed Q only, so this blue will change into green because now you have changed this theta, right? So this L is a function and functional. So once you change that your theta, this blue will change into green, and then you maximize over it. This is your new theta, and you keep on doing till you come here. So it is a, you maximize it and it will maximize till your local maximum, right? Till your local maximum. So you just see, try to digest it. It may not be very easy to digest, but I don't think so that it is too hard to understand also, right? Any question on this? Can anybody tell me why I am getting like what what is being changed when when this blue curve change into a green curve? What exactly I have changed just to make this blue curve to the green curve? It is being shifted. I have shifted I have tuned something here, right? So what do you think I have changed here just to make this green curve into blue curve? No, that's fine. So I am trying to show you here that L, this lower bound is a function, right? Function and functional. So if it is a function, then you see that this blue, you change your theta, you change your theta, and you have fixed your q, right? You have fixed your q. So once you change your theta, you are moving on this curve like this because you are changing your theta. So your q is fixed, right? And if your theta is fixed and you are moving your q, right? If your theta is fixed and you are moving your q, so now once you come to this theta new, because you have maximized this ql here, and then you are changing your q. The moment you change your q, what will happen? This blue will turn into green with this move like this, because it is a functional of q also. Once you change q, you are moving in this direction, right? On this blue curve itself. The moment you change your q, your this L, which is represented as a functional, now it just changed its form and it will become the q. So it is a family of these so many curves. So I can understand it is a bit hard, but if you want to draw in this that it is a function of q, so this is q1, this is q2, this may be q3, this may be q4, this may be q5. Fixing your theta, so theta is not being changed here, right? But the moment you change your theta, fix your q, you are just moving on one particular graph here. So you just spend your time here. Yes, you spend your time here. So this is all. Okay, so now let's, though I have already told you these things. So this was my Gaussian mixture model. I told you that in expectation step, what I am doing, this is my posterior, which I am calculating here, right? The moment I calculated a posterior, then I need to calculate the expectation of that with respect to this posterior, right? So the if I calculate the post expectation of the my posterior, so I have not written. So this was my, okay. So this was my thing, right? I said, I think I forgot to write it. So this was my probability of x comma z, right? How I can write it? So this is first I need to calculate the probability of joint, probability of x comma z, right? Then I marginalize over z, and then I multiply over all these things. So this is nothing but it is a probability of x given theta, right? So if I want to maximize my expected log likelihood, that is incomplete. So I want to write this first. So this is my x comma z, right? X comma g is nothing but you can write it this way. So it is a product over k, right? Then it was pi, that was pi, right? Multiply that normal, right? And you just add that z k, right? So this is pi k and nk, right? So this was a giant probability of x comma z for one sample, and for all samples you do this thing, right? For all samples, and if you take a log of this giant probability, what you will get? Summation over n, right? Then it is summation over k, right? Then it is z k. Then what will happen? Log pi k plus log nk. Log nk means it is a normal distribution, so log will cancel that exponent. Log will cancel that exponent, and that the inner side of a quadratic form will come here, right? And if you maximize this with respect to mu, which comes somewhere here inside this, you will see this form, right? Because you have taken expected value of z from here, right? So tomorrow I will show you that slide. I hope that I missed that slide somewhere. Okay. I think this is there. What happened? You calculated your posterior probability, right? So how you calculated your posterior probability? This is your joint probability, right? And this is your marginalized probability. If you solve them, this is how you can write it. And finally, it is nothing but the joint probability for all posterior is nothing but the product of individual posterior probability for every sample, right? And if you once you know this, right? Once you know this, then you just had this in log complete likelihood function, right? You had this complete likelihood function. When you take a log of this, you have this thing, this form, right? Okay, you have this form. And because I said that you need to calculate the expected value, so expected with value with respect to this posterior distribution. So here I was not aware what was the value because it was incomplete. So I need to replace this expected value here, right? So the moment I replace this expected value, what I will get? This is the same thing. What is this? This is you just note this. This is this q theta over theta. So this is this thing, right? So this is q old theta, which is nothing but this, which is a expectation of incomplete data likelihood, which you have seen. So hence you are saying that your expected Gaussian mixture model, you are doing the same thing, right? Okay, then you just take, I will distribute these slides to you. You just go through it, and I will try to go one more time over this last few slides, right? You just spend a few minutes, few hours on this, and then I will cover this same thing tomorrow in first 15 minutes, and then we'll see like what to do. Okay then. Drop your attendance. Thank you very much.